Today's webinar is going to be given by Alex Duke, who is a research associate at the University of Edinburgh in Paul Patra's team. He is deeply involved in developing Microscope, which is a patent pending technology that was launched by NetAI, a university spin-out. In 2015, Alex drives the research and innovation strategy in an IoT design house, where he collaborates with academia to bridge the gap between IoT, cybersecurity, and machine learning. He received a PhD in computer science from University of Lyon, and during his PhD, he developed a patented technology that allows bidirectional visible light communications for IoT devices. This technology has now been commercialized under the brand Kiwink. His research interests are at the crossroads of wireless communications, Internet of Things, machine learning, and cybersecurity. In today's talk, Alex will present an original deep learning approach to service level demand estimation that relies not only on total traffic aggregates. Experimental results with metropolitan-scale network measurements will reveal that the proposed solution infers per service traffic demands with 99% accuracy. So I would like to welcome Alex. Good afternoon, Alex.
Okay, thank you, Thomas, for the introduction. So before we start, I would like to remind that this work is a 3-year research with my teammate at the Mobile Intelligence Lab in the University of Edinburgh. And it's a result of a collaboration with Paul Patras, Xiaoyun Zhang, and Marco Fiore. So before going to the detail, I would like to just put a little bit of context. So this work is based on the observation that mobile networks are going to be a general purpose technology used in different scenarios, different situations. And so we will have to accommodate with a different range of services, with different performance requirements. This include applications like, let's say, autonomous vehicles, industrial automation, smart health, Internet of Things, and so on. And this type of applications pose requirements that range from very low latency to enhanced capacity, ultra reliability, and many other. And accommodating this diversity of performance requirements, it's only possible if the management of the network resources become more intelligent. And to make this possible, a new architecture paradigm has been introduced with 5G. It's called network slicing. And network slicing allows to logically partition the physical infrastructure of the network into different virtual networks that we call slices, and each slice can serve a dedicated service and have its own resources. So, for example, you can have a slice that is dedicated to video streaming, another slice that is dedicated to industrial automation, another slice for, let's say, autonomous vehicle, and each slice have its own performances requirements, its own service layer agreements. So a slice can be optimized for very low latency, while another slice can be optimized for enhanced capacity. This new paradigm of network slicing is expected to reduce the total cost of ownership up to 50%. But the challenge to make this possible is to obtain in real time the information about the nature and the origin of the traffic that flow over the slice, to be able to, let's say, effectively manage, monetize them, and to be able to put at the right moment enough resources to reduce the cost and make the make the user satisfied. And the current approach for knowing the traffic that's come to the different slices is based on a deep packet inspection that we also call the DPI. There are different kinds of DPI. So the first one is hardware-based DPI. But the main problem with hardware DPI is that it's very expensive because it uses specific hardware like FPGA. It costs a lot of money, so it's not really scalable. It's impossible to update. And the problem with FPGA is that when you introduce a new protocol, you have to change the hardware. So it's very problematic. So another approach, and many people are interested in that, is a software-based DPI. So the deep packet inspection is performed by a software, by the operating system, but the main problem here is that it's very slow because you have to capture packets, put it into a queue, and it introduces a lot of latency. Sometimes you can lose packets, so it's not very efficient and not very reliable. And also both approaches are becoming impossible when the traffic is encrypted. And you know, today more and more traffic are encrypted. So deep packet inspection can be problematic to make network slicing and make network automation something possible. So that's to solve this problem, we propose a novel approach that is the mobile traffic decomposition. So what we propose is to break down traffic aggregates into different time series that correspond to different services. And we would like that to operate at different level. So we can collect aggregates at the level of the base station, but also at the level of a cloud data center or at the level of mobile edge computing facilities. And so there we would like this to work even with encryption, with different application scenarios. And this work will exploit the spatiotemporal collaboration we have and that are characteristic to mobile network traffic. Because you know, when you are in the cities, people move with their smartphones and will use different services according to their motions. And there are some temporality in the motion of people and in the usage of a specific service. So for example, when people travel to work, they will watch videos, they will listen to music, and while when people are working, we will see that some video conferencing services will be more use than, for instance, let's say, video game um, or others. But decomposing traffic aggregates can pose different challenges. So the first one is that when you want to decompose a signal into multiple time series, in fact, you can have multiple solutions. And also capturing complex spatial and temporal correlation to resolve this ambiguity is not trivial. There are several techniques that are being used in other domains for time series decomposition has been used, like the factorial hidden Markov models, but they work on a single time series. But here we would like to make them working for multiple time series. So our goal here with this work is to decompose multiple input time series concurrently at different network locations that in our case are the different, let's say, at the different base station or at the different data center. So to solve this problem, we propose an original dedicated deep learning framework for mobile traffic decomposition, and we called it Microscope. So we see here that we would like to collect some time series and mobile traffic aggregates at the level of antenna that are point clouds, and point clouds can't be directly plugged into convolutional neural network and other neural network model. So for that, for before putting it into our framework, the first step is to convert these traffic measurements into a format that is suitable for analysis without losing geographic information, because as I said, a key characteristic of mobile traffic that we would like to exploit is a spatiotemporal correlation. So the first step of our to our framework is to proceed to traffic snapshot transformation using the Hungarian algorithm. I will introduce it a bit later. Then once we have converted our data to a suitable format, we put it into a neural model for mobile traffic decomposition inference. And our approach is quite flexible, and we are able to use different kinds of neural network model, like LSTM, like convolutional neural network, and other work that we have proposed before. And since it's not only we also propose our own neural network model that is specifically dedicated for mobile traffic decomposition. And then we use a different loss function. We test different loss function to drive the training process. And we perform some output normalization to increase the performance. And finally, we obtain at the output of the framework the estimated service snapshot. So just to sum up, we start with aggregated traffic spread over a point cloud, and then we would like to obtain a specific service snapshot for the different service. So we start with aggregate, and then we obtain different services like YouTube, video streaming, Spotify, gaming, etc. So now let's start with the first step of this framework, that is the point cloud to grid transformation. So here, remember that we are collecting the data spread over open clouds that are basically antennas, base station of the mobile network, and we would like to convert them into a grid. So for that, we construct a regular grid that has the same number of points of the number of antenna. This format is suitable for convolutional neural network and the convolution operation. And then we perform a one-to-one association between these point clouds and the grid, and we try to minimize the displacements of the original location to preserve the spatiotemporal coloration, and because this characteristic that we want to exploit later. And for that, we are going to use the Hungarian algorithm that can be run efficiently in a polynomial time. Then, after we have obtaining this individual, we have put the input format into a suitable format for the neural network. We are ready to use it into our 3D deformable convolutional neural network that is an original class of convolutional neural network that is designed for the purpose of mobile traffic decomposition. So here we are taking the inputs which are basically sequences of multiple traffic aggregates that we are converted into a grid, and we will then pass this input sequence of the aggregate traffic snapshots into different class, different layer of convolutional neural networks, and the output we will obtain traffic snapshots that correspond to the individual mobile services. Our first block of 3D convolutional blocks, we will use different stacks of the 3D deformable convolutional layer. Then we'll pass it into batch normalization that will improve the learning times. And then we have the liquid ReLU that we will use to make it more efficient. So now let's get a closer look at the novel component that we have introduced, that is the 3D deformable convolutional network. So if we start with, if we want to perform a vanilla 3D dimensional convolution, we will have basically a 3-dimensional filter that is compact and like a cube, and we would like to use this filter to scan the inputs at the different location in 2 dimension, and in 2 dimension because you have 2 dimension for the position and 1 dimension for the time, because we are taking a snapshot of historical data. So instead of applying this compact 3D convolution filter at different location, we would like to use a deformable filter, and to do that, we will introduce some offsets that are applied to the filter, and these offsets we will learn them during the training process. And we will apply this filter with this offset to the different inputs of the network the different inputs of the 10 inputs. And since this offset will be there for introducing a new degree of spatial and temporal correlation that exists in the different locations in the inputs. And then after obtaining this offset, we have a deformed convolution filter that we will use to scan the different inputs, and it will be apply a convolutional operation using scanning inputs that are not adjacent necessarily, and so it's like it is like some it's like the different location are not adjacent. So it will try to reconstruct and to remove the distortion that we have introduced just before with the Hungarian algorithm by the transformation from point cloud to a grid. And then finally, at the output of the 3D deformable convolutional neural network, we obtain an abstract map that corresponds to the different services. And there are some kind of different abstract feature. And after performing and then after obtaining that, we implement this framework, Microscope, using TensorFlow and Tensor Layer. We trained this framework and this neural network using different loss functions and the add-on optimizer. For that, we use an HPC cluster with GPU, and we use a data set that has been collected by a mobile operator in a large city over 3 months, and we focus on 9 services, and the services are video streaming service like YouTube, audio streaming like Spotify, web traffic like Google, social media like Twitter, Facebook, Instagram, Snapchat, and also some video game like Supercell and so on. And we evaluate the performance at different network levels. So at the base station, in the case of mobile edge computing facilities, in a cloud run, or at a core data center. So now let's focus on the performance evaluations at the base station. So we evaluate the performance in terms of the mean absolute error and the normalized mean absolute error between the ground truth and the ground truth and the traffic per service consumed by each individual traffic services. We use different loss function like the regression, the mean squared error, and the cross entropy. And we see that the performance we also use our framework with different kinds of neural network. You have here the MLP, the multi-layer perceptron. That is the most simple neural network you can have. We use also CNN that are a kind of neural networks that are often used for image recognition. We also use recurrent neural network like LSTM and Convolution that are a kind of neural network often used for time series processing and prediction over time series. We implement our framework with ZipNet. That is a kind of neural model that we have developed in one of our previous work for mobile traffic over super resolution. And finally, we use our 3D deformable CNN that I have just introduced before. We see that the different loss function perform differently according to the kind of neural network model. For instance, you can see that regression is better with the MLP, the multi-layer perceptron, while in our case, for the 3D of CNN, it's the cross entropy loss function that perform the best. And we see that our approach, the 3D deformable CNN, performs the best and has a very high accuracy and can infer and decompose the mobile traffic with less than 1% error. Let's now focus on the performance for the different service. We can see here that the mobile traffic decomposition perform pretty well for all the service. For a streaming service, we can see that the mean absolute error is high, but it's because the volume of the total traffic is very large. And if we look at the normalized absolute error, it becomes as low as the others. Now let's have a look on the results on only one test week at a single antenna. So here you see the time series for the aggregated traffic during 1 week at a single antenna. And this is a time series that our framework can decompose into different services. So here you can see the time series of the decomposition for Spotify, Snapchat, and Facebook. And we compare the ground truth with the prediction. And we can see that our framework decomposes pretty well, and the prediction follow pretty well the ground truth, even for service like Spotify that presents frequent fluctuation. So we see here is that even for the spike, our framework and the prediction follow pretty well the traffic profile. We also now look at the traffic decomposition at the data center level. So we look at the impact of performing decomposition for different cluster level. That's what you are looking here in the different color. We are looking at core data center deployment, where the city is covered by 10 data center, which are serving the entire deployment. Or we can have 30 cloud run data center that to cover the city, and we use different color for the different cluster we obtain. And to obtain the different cluster, we would like to perform antenna assignation to serve a comparable traffic loads while minimizing the latency, that is the distance between the different antenna and the core of the cluster of the data center of the MEC facilities. And to do that, we used the CAV fast flow partitioning heuristic that tried to minimize the distance between the different cluster points and optimize and reduce and to serve and to load balance the traffic over the different cluster. And for that, we use we study the performance with different resource orchestration interval, because if the traffic is accumulated in a data center, we will basically consider wholly orchestration interval, while at a lower granularity at the base station, we would like to perform mobile traffic decomposition at high frequency, for example, from 5 to 30 minutes. The main insight here is that the LSTM is sufficient for the estimation of per service traffic consumption if we look at a core data center level, irrespective of the temporal granularity. So that means that it's not necessary to use our complicated and a complex approach that like the 3D deformable CNN that we have proposed. If you want to achieve mobile traffic decomposition at core data center, so you can use something that is simpler and more effective. But if you want to perform mobile traffic decomposition at high frequency at a lower level, for instance, at a cloud run data center, or at the level of an antenna of at mobile edge computing facilities, it's better to use the 3D deformable CNN. And whenever where you perform the resource management, when you do it at a longer interval, LSTM is sufficient to do that. We now study the complexity, and we now analyze the complexity of the different neural network that we have plugged into our framework. And for that, we study the complexity in terms of the number of floating point operation. That is a metric that is commonly used for evaluating the complexity of a neural network model. We study the complexity at different location. If the mobile traffic decomposition is performed at the antenna level, of it is performed at the level of a data center. And we see We see here that the computational requirements of convolutional neural network model are surpass those of LSTM only for antenna level, because you see here that the neural network that are based on convolution operation are very sensitive to the granularity. We also see that the complexity of LSTM doesn't depend of the location where you perform the mobile traffic decomposition. And also you see that the complexity of our approach, the 3D deformable CNN, is higher than other approach only at the antenna level. But if you perform that at the core data center level, it becomes very efficient. Also, if we look at the right plots here, we see that the complexity of the approach we have proposed, the deformable CNN, doesn't the introduction of the deformable convolutional blocks is not very important compared to vanilla convolutional blocks. And so finally, we evaluate the cost introduced by SL evaluation or over provisioning due to the mobile traffic decomposition error. And our insight here is that the person cost at core data center is between from 8 to 58% when computed with respect to the true domains. And in fact, when we compare that with the state-of-the-art predictor, we obtain better performance. And if we look at the antenna level, so here it's not SL evaluation or over provisioning, it's basically additional throughput. So it's additional spectrum. It should introduce additional CPU time. And we see here that our approach leads to only 7% of additional CPU time that correspond to 6 megabytes of throughput. So here we see that mobile traffic decomposition and Microscope is very promising, and it's a viable low-cost approach to service level demand estimation in practical network management and network automation. To sum up, Microscope and this our framework. So we have introduced an original deep learning approach for service level demand estimation that rely only on the total traffic aggregates. And we see that this has very high accuracy. It can estimate the per service traffic demands with 99% accuracy. Microscope can incorporate a different neural model that can be to adapt them to different management location or different time scale. We see that LSTM can be used when we want to perform mobile traffic decomposition at a core data center without the needs of high precision. And if we want to see to perform mobile traffic decomposition with a high granularity very frequently or at the base station level, we propose for that the 3D convolutional neural network. And the experimental results with a true dataset, with a dataset that has been collected by a mobile operator, show that it's very accurate. And finally, Microscope can help, and we hope that it can help a mobile operator to solve the computationally intensive traffic analytics that is a key a need that is a need for resource provisioning in 5G and to enable network slicing. And all this work is a patent pending technology, and it is at the core of NetAI, a University of Edinburgh spin-out. This ends the first part of my presentation. I will be happy to answer a question after the webinar. So if you have questions on the Microscope and on this first part, I will encourage you to ask questions and to ask questions in the Q&A section of the webinar. So now let's go to the second problem that we would like to solve. And I talked about it in this first session, is how we can use spatiotemporal datasets with a neural network model and use datasets that are basically point clouds time series. So how we can learn on point clouds. So this work, we will introduce a dynamic convolution operator that will resolve the grid structural data requirements of existing model. And we will show that this operator can be easily plugged into traditional neural network model like LSTM. So how we can learn spatiotemporal feature over time. So how we can do that. So remember that mobile traffic datasets and their analysis needs the spatiotemporal correlation and the configuration of the data points over time to be preserved. All the approach that has been proposed for spatiotemporal inference require grid structural data. That is the case of convolutional neural network. So before feeding the dataset and the input time series into the neural net model, data processing is so required. And an example of this transformation is the Hungarian algorithm that I introduced in the first part of the presentation. But this transformation introduce some error into the model. So our goal here is to eliminate the needs of the data preprocessing, conserving the spatiotemporal correlation. So to sum up a little bit how the data come to the mobile traffic, the mobile data set are. So basically, we have a set of antennas that are spread over the city, and obviously they are not spread in a grid manner, but they are deployed by the mobile operator to manage the traffic loads. Also, they are placed in a location where it's suitable to have an antenna. So we can see that as geospatial point clouds. So different approach for the transformations of point cloud to grid has been proposed. So to forecast on a grid, basically that's what convolutional neural model does. For instance, for video inferencing, image recognition, and so on. The other way to forecast an antenna is to do some transformation before using the data into the neural model. That is exactly what we have done before in Microscope. So we perform some transformation, but there, with the transformation, we introduce some error into the data sets, and so we can lose the spatiotemporal correlation that are very important for mobile network inference. So in this work, we propose to perform forecasting directly over point clouds. So for that, we introduce a novel convolution operator that is a dynamic point cloud convolution that we called D-Conv. So D-Conv is able to perform convolution over a point cloud. That is what you see here. So basically here you have a point cloud that is our data set. So each point P is a tensor with which contains a coordinate feature that is C. So basically the position, the coordinates of the antenna in the city. And also you have the V that is the value feature, and we can accommodate with various features. So for instance, for mobile traffic is the total aggregate traffic that we have for a specific time interval at the specific location. But it can also be the, let's say, a sensor of a city, a pollution sensor of the temperature at a certain place in a city. So the first step of this operation is that for each point P, we define and we pick a k number of neighbor. So we define a set of neighbor, and then for each point and each neighbor set, we perform a weighted summation over this neighbor set. And for that, we use a vector V, which are the weight for the different neighbor offset. And this weight, the weight you see here, the WK, the WK6, WK2 are learnable weight. And we will try to learn during the training process the weight. And this vector of weight is shared across the different points of the data set, and we will use it to compute a weighted summation over the k-neighbor sets to obtain the output point Pn here. So this transformation can change at each time step, can change the location of the original point P. And we repeat this process for every point P with the same shared weighted W to obtain the output map as out that you see here on the right. And then we use this dynamic point clone convolution. Deconv, we plug Deconv into a vanilla LSTM cell to create the CloudLSTM cell LSTM cell that you see here. So this is basically a classical, the original LSTM cell, except that we use our Deconv operator here. So you have, you can see here that you have like LSTM cell, the input gate ET here. You have the output gate. You have FT that is the forget gate. You have CT that is the memory cell, and HT that is the hidden states. Remember that here, ET, FT, OT, and CT are all point clouds representation. So now we combine this clouds LSTM cell to create the sequence-to-sequence model that you see here on the right. And we use the soft attention mechanism that has been proposed by Long to perform forecasting. And we use this kind of neural network model because it has proven to be very effective in spatiotemporal modeling on grid structural data. So you can see that the architecture here incorporates an encoder and a decoder, which are different stack of CloudLSTM cell. So the encoder encodes the historical information into a tensor, while the decoder decodes the tensor into prediction. And you see here that the encoder and the decoder are connected using the soft attention mechanism via the context vector. And before feeding the point cloud to the model and generating the final forecasting, the data is processed here by the point cloud's convolutional layer. And it performs the Decompos operation that we have seen. So now we will evaluate our neural model using datasets of mobile traffic data that has been collected in 2 large European cities for about 3 months. We collect the data has been collected for 3 distinct services, like for Microscope. And we use, in the first time, we use 30 minutes of data to forecast the following 30 minutes of traffic for the different services. So now let's have a look at the results. So we have implemented Deconv, and we compare the performance with a different kind of neural network that has been proposed for mobile traffic inference. So we have the MLP, the CNNs, a different kind of CNNs, different kind of recurrent neural network like LSTM, RNN, also GRU. We see here that models that are based on convolutional neural networks like CNN, 3D CNN, Cloud CNN, has a mean absolute error that is higher than models that are as based on recurrent neural network. Maybe this is because CNN and a convolutional neural network fail to capture um, the time dependence and can't capture the time series. And we see that also the approach that use our Decompos operator perform better than the others that use vanilla convolution. And finally, we see that using the attention mechanism, we obtain a very low absolute error. And we compare also with another city, and we see quite similar results, even if for some neural network models, the results are quite different. But we see that for all the cases, the CloudLSTM and the attention CloudLSTM that we have proposed offers the lowest prediction error. We also look at a long-term prediction. So if we want to perform prediction, long-term prediction from the 30 minutes to more than 3 hours, and we see that even for long-term prediction, using the same input length, the results are very promising. And the mean absolute error remains very low. And something interesting that we can see is that for long-term prediction for the CT2, a large case, so that means that if we use a larger number of neighbors in the Decompos operation, we obtain a better performance. But basically, if you want to perform short-term prediction, when we see that the number of neighbors doesn't influence the performance, it's better to choose a lower key because it will reduce the computation complexity. So to sum up this work and D-Conv and the CloudLSTM, we have introduced D-Conv. This is an operator which performs convolution over point clouds directly without the need of transformation. And Decompos can learn special feature while maintaining permutation invariance. We see that Decompos can be easily combined with different kinds of recurrent neural network model, like RNN, GRU, LSTM, sequence-to-sequence learning, and it can be used with attention mechanism. We use Decompos to build CloudLSTM, that is a dedicated neural model for spatiotemporal forecasting, specifically developed for mobile traffic inference. CloudLSTM can also be used with other kind of geospatial spatiotemporal datasets, for instance, for pollution forecasting or temperature forecasting in a city. And we have also some interesting results about pollution forecasting in a city in some of our paper. And we see that the experimental results using real-life datasets, that our approach outperform state-of-the-art for mobile traffic forecasting. If you want to know more about this work, about mobile traffic decomposition, and about CloudLSTM and Decompos, and our work on mobile traffic analysis and deep learning. You can have a look at our paper Microscope that has been presented at Mobicom this year. You can also read the CloudLSTM paper that is available online on Archive. And more generally, if we want to follow our work on mobile traffic analysis and deep learning, you can go to our website of the Mobile Intelligence Lab following this link. And finally, if you are interested in what we are doing at NetAI, we are developing a university spin-out, and we are welcome to any suggestion, partnership, collaboration, or investment. And you can you are free to send us an email if you are interested. So thank you for your attention. Feel free to ask questions in the Q&A, and I'm now available for discussion and to answer your question.
Thank you so much for the wonderful presentation, Alex. Now I will switch directly to my colleague Vishnu to take over during the Q&A session. So Vishnu, welcome and good evening.
Thank you, Thomas. Thank you, Alex. I think that is a great presentation. Let me just look at a couple of important questions because we are running slightly out of time. The first question is about what exactly are you predicting? So I think in the D-Conv result that you showed in one of the slides, you had actually shown the 30 minutes plus 30 minutes. That is the kind of prediction that you're trying to do. Is that for the mobile services that you showed? Is that same for both the approaches, Deconv and the CloudLSTM, or is there something else? What kind of prediction are you trying to do?
Yeah, so basically, CloudLSTM is using the Deconv operator. So CloudLSTM use Deconv. You can't use Deconv without a neural network model because Deconv is only an operator. And what we are predicting is that we use 30 minutes of data to predict 30 minutes of traffic for the different services. So basically, we use 30 minutes of, let's say, YouTube traffic, and we say that at this specific location, we will have in the next 30 minutes, let's say, 10 megabytes of YouTube traffic. But this can also apply for the pollution. So we can use, we can have, let's say, okay, we have in the last 30 minutes of there is a certain level of pollution at this place. So what will be the pollution level at the same place for the next 30 minutes?
And in one of your early slides, you mentioned about the effect of encryption. How does your technique work with respect to encrypted traffic?
Yeah, because in fact, Microscope doesn't rely on the content of the traffic because it's only aggregate. So the inputs of Microscope is only, let's say, it's a volume of traffic, so megabytes of data. So we don't need to know what is in the packet. So even if it's encrypted, it doesn't matter for us.
One of the question is about using IP layer information. Could you comment upon whether inspecting IP headers, for example, can you can you find out from the IP headers that what kind of service is being used, and how Microscope is different from using this IP layer information?
Okay, so basically we don't like it's my my answer will be close to the answer for the last question, because we don't look at the IP packet or the IP header, and we just need volume of traffic, aggregate of traffic. So our approach don't use either or thing like that. Do you see what I mean? Do you see what I mean? Is it clear?
Yeah, I think it is quite clear. So you don't look at individual packets, you look at aggregated traffic. Yeah. My last question is about rare events, because I remember reading the Mobicom paper when it came out. And one of the important questions, I remember the graph, which Paul had also pointed out in his YouTube video. It showed that in case of rare spikes, you are not able to predict accurately the rare spikes. Once in a while it goes up, and the performance of the technique does not really match up. Could you comment on this particular behavior?
Yes. So basically, I think that is the case for Spotify, because Spotify, we can see that there are a lot of variability in the mobile traffic, but I think that we don't capture pretty well the spike, but in fact, when the behavior still follow pretty well the curve, and when you want to forecast the traffic, and when you want to allocate resources for a specific slice, for instance, you don't need to really look at the spike, because in fact the load will be spread over time. And also the spike, even with other kind of neural network model, it's something that is very hard to capture. So yeah.
Okay, that's a great. That's a great answer. Thank you so much, Alex. We are out of time. Yes, yeah. Thank you for staying back, and we have a good discussion and a great presentation. There are a bunch of references on the chat window. Thanks so much. Over to you, Thomas.
Thanks a lot, Vishnu, for the quick going through the questions very quickly and brief. A very big appreciation to Alex for the wonderful talk, harnessing deep learning for mobile service traffic decomposition to support network slicing.